Good morning. My name's Brian Wheeler. I'm the program director at Save Wild Trout, and I want to take the chance today to talk to you about our water quality monitoring project throughout the Jefferson River Basin in southwest Montana. Save Wild Trout officially became an organization just a couple years ago in 2023. Um, but the story starts long before that, and I'd like to chat about the genesis of this project, from its origins with the Big Hole River Foundation, how Save Wild Trout got its start, what work they began doing, where we are today, what we've been finding in terms of water quality in the Jefferson Basin, and then where we might be able to take that information and go from here. So it began in 2019 under the Big Hole River Foundation when that group began to search out where were the data gaps, what was missing, what information didn't we have that might help in terms of fisheries management and resource protection. We figured out essentially that nobody was collecting water quality data, and that was an important missing piece in terms of fisheries management. And so that project design began and was refined throughout the following 6 years. And during that time, Save Wild Trout began as well addressing some other data gaps. In May of this year, the two organizations merged because we recognized both the utility of the water quality monitoring projects, their importance, and the fact that other rivers needed these projects to inform management. And the purpose, of course, was to address data gaps and expand, and that's what we've done, beginning specifically in 2025. But I'll talk to you about how we grew even before this year. Now, first, we have to talk about the Jefferson watershed. It entails the bulk of southwest Montana. I've got it outlined there in blue, and it's really hard for folks not from Montana or the West in general to understand how geographically expansive this region is. We're talking over 9,000 square miles, nearly the size of the state of New Hampshire, and it incorporates 4 primary rivers, the Big Hole, the Beaverhead, the Ruby, and the Jefferson itself, and contains the bulk of the headwaters of the Missouri River system. And one of the things that makes this watershed so ecologically unique is it is the last remaining refuge of a remnant population of native Arctic grayling, who at this point in time are relegated to a mere 5% of their historic range. So this is a region of Montana that is both ecologically and economically important. So we got to ask ourselves, why even bother monitoring water quality? Well, number one, nobody else is doing it. And certainly nobody's doing it on a long-term consistent watershed scale. There have been efforts associated with individual restoration projects and things like that. They're short-term in duration and narrow in scope. Secondly, if we're not monitoring water quality, just like we monitor our fish populations, we don't have baseline conditions against which we can determine whether things are improving or deteriorating. Thirdly, it's important for resource managers and stakeholders to have objective evidence about the condition of our resources, both today, historically, and hopefully gaining a picture of what emerging trends are happening that might influence that water quality in the future. And finally, as I noted earlier, these are such economically and ecologically important resources that they require proactive science-based management. We want to get ahead of problems rather than react to problems. And, from a legal perspective, the Clean Water Act says that all surface waters of the U.S. are designated with specific beneficial uses that they're required to support. And that includes irrigation, recreation, drinking water, and aquatic life. And so from a legal perspective, monitoring water quality is an essential function. So how did we get here? 2019, as I noted earlier, Big Hole River Foundation created this pilot project on the Big Hole River. First, we had to determine, okay, where are we going to sample? How many sites are we going to sample at? A big part of that had to do with what can we afford to do. Secondly, we wanted to consider what kind of distribution of sites would give us a good picture of land use changes and influxes, in particular, of nutrient pollution off the landscape. And that gets to point number two, the analytes. What are we going to sample for and get analyzed at the lab? Because nobody had really focused on nutrients, and by nutrients I mean primarily nitrogen and phosphorus, prior to this pilot project, that was an obvious choice for us to design the project around. And then thirdly, we had to decide how often are we going to sample, both in terms of frequency, but also throughout an entire season. You can see this map here. This was our initial project design, had 8 sites, from Jackson up near the headwaters all the way down to just above the confluence with the Beaverhead and the mouth of the Big Hole. We had 8 sites, pretty good distribution, a couple of primary tributaries in there, and this was our starting point. In the spring of 2020, after we had operated this pilot project for an initial year, things got credible. They got valid. They got approved. In April of 2020, this project was approved by Montana's Department of Environmental Quality, DEQ, and we designed a sampling and analysis plan that was reviewed by a technical review committee at the state and approved prior to the project beginning that year. That kicked off our official partnership with DEQ as a member of their Volunteer Monitoring Lab Assistance Program. And as a result of that, we had both technical support in terms of designing a sampling and analysis plan to create a good project, but it also gave credibility in terms of meeting very rigid scientific standards for our methodology of the field program protocols, lab analysis, and not only data analysis in that sense, but also the obligation to upload that data at the end of each year to the state water quality portal, at which point the state would review, approve, and that data set actually goes on to the national EPA water quality portal. So 2020 was a big year for that project. We also began working with the Montana State University Extension on water quality, both for data analysis and trying to figure out where are we going to house this beyond the state water quality portal that folks might be able to tease out and look at and visually graph what we've been collecting. Then in 2021, after the initial approved project year, we grew. We gained some new partnerships. The most important ongoing partnership that began in 2021 was with Flathead Lake Biological Station as a member of their Monitoring Montana Waters program. This not only helped us gain some lab analysis funding and continued technical support and a secondary group to review our sampling and analysis plan prior to each year's program. But it also gave us a couple more PhDs to supervise in a capacity related to their specialties. And Dr. Rachel Mallison from the Flathead Lake Biostation is an entomology specialist focused on salmon flies and stoneflies. And so what a perfect fit for the foundation. This new partnership allowed us to grow in a couple of ways that were really important. In 2020, the first year that the project was approved, we saw some really high levels of nitrogen and phosphorus in the upper river. So we wanted to flesh that out a bit. We were able to add a sampling event both in April prior to runoff and also in October to characterize water quality during the primary month of the brown trout spawn. And the reason we go from April through October on the Big Hole River is because as a freestone river, it's extremely dynamic hydrologically. And what I mean by that is during snowmelt, rain, spring months, we get a spike in the hydrograph, it drops again, and it fluctuates throughout that spring as we get precipitation, melt, and falling events. And then once we get to the summer, we are primarily concerned with the base flow months of July, August, and September, where there's very little change in that hydrograph. And that's also the months, or the time frame rather, that DEQ is concerned with as it relates to potential impairment of rivers or stretches of rivers for pollution. Secondly, related to what we found in that initial 2020 approved project, we wanted to attempt to narrow down the areas where we were seeing those really high levels of nitrogen and phosphorus. And so this new partnership with the Flathead Lake Biostation allowed us to add 2 new sites, one on the North Fork of the Big Hole, another primary tributary in the upper river, and then a sort of control site at the very, very, very headwaters up at Skinner Meadows, largely above most human and cattle influence. So from 2021 on, this is what our project has looked like in terms of site distribution and number. We have 10 sites from the headwaters to the mouths, and we have 7 sites on the main stem of the Big Hole, and we have 3 primary tributaries covered in the North Fork of the Big Hole, Deep Creek, and the Wise River. So from 2021 on, this is what our project site distribution looks like on the Big Hole River. Okay, we've discussed how we built the initial pilot project, what we decided to look at, our site number, our site distribution, our site visit frequency. We can't really go any further without discussing the importance of those pollutants, and make no mistake, pollutants include things like nutrients, temperature, sediment, as well as the classic known pollutant of heavy metals in Montana. But without understanding how the state and water quality is impacted by these, we have to preemptively discuss what do pollution diets look like, and that's where TMDLs come in. This is a total maximum daily load. How much of a pollutant can a river system or stretch of a river system absorb before experiencing negative impacts on those beneficial uses we mentioned earlier? In the Big Hole, we have 3 different planning areas, and you saw in our site distribution map, we covered those thoroughly, the upper, the middle, and the lower sections. There are existing impairments on the Big Hole, primarily for sediment and temperature. A lot of the tributaries have impairments for heavy metals where there was historic mining. A lot of reclamation work has been done on those tributaries. But the point is, without regular monitoring to document either improvement or deterioration, we're unable to quantify whether these stretches of the river are meeting these pollution diets and whether they should be designated as impaired or retain impairment status if it exists, or if they've improved to the degree that we should be removing these stretches from that 303D impairment list. Again, I will harp on this all day. Without regular monitoring, we simply can't achieve these requirements. Why are we concerned about nutrient loading, nutrients as a pollutant? Well, as you can see, the proof's in the pictures here. We got in the top couple of pictures, the bright green neon algae bloom, that's from the Middle Big Hole in 2020. Those bottom 2 pictures are actually a harmful algae bloom, a HAB, that is cyanobacteria, blue-green algae, on the upper Beaverhead in 2019. So these are the reasons we're concerned with nutrient overloading in a river system within the Jefferson Basin. Nutrient loading is a stressor. The response to that stressor, along with some other variables, is an algae bloom like this. So nutrient pollution and overabundance of nutrients within a water body, primarily nitrogen and phosphorus. Eutrophication is the process by which that water body becomes overly enriched and saturated. Um, it can happen from natural means, weathering of rock, erosion, things like that. Primarily, though, this happens from human land use patterns and what we would call artificial means. Certainly, you can see that this has harmed water quality. So that's one of the concerns of eutrophication. And when water quality is diminished to the point that you get these really big algae blooms, you have some other related problems that compromise further the condition of your watershed, in particularly as it relates to supporting aquatic life. And that is due to the process of photosynthesis and respiration. When these algae bloom and grow during the day, during the sunlight hours, they're engaged in photosynthesis. Imagine these algae within a water body as a giant set of lungs. During the day in photosynthesis, those lungs are inflating. Those algae are producing dissolved oxygen. You can literally see this in the hydrograph. During the day, when there's a really extensive algae bloom, you can see that graph bump up even in the low flow months, even when there's been no precipitation. And that's because this inflating set of lungs of aquatic plant life and algae literally displaces water and changes what the hydrograph looks like. And the flip side of that coin is at night, when these algae are respiring, that process is consuming dissolved oxygen, and it's like a deflating set of lungs. And you can see this again in the water table in the hydrograph as that volume drops again. And then secondarily, beyond that photosynthesis and respiration process, you also have the process of decomposition when the algae die. That process itself consumes dissolved oxygen. And so you kind of get a double whammy with algae in terms of crashes at night in dissolved oxygen, and then crashes again at the end of the season when they let loose, die, and begin decomposing. Why is dissolved oxygen a concern? Because when you get really low levels of dissolved oxygen, it has negative impacts on aquatic life. And it can compromise both fish and the bugs that fish eat, those species' ability, their metabolic processes like growth. It can affect things like their respiration and reproduction. So those negative impacts are very concerning on aquatic life as a beneficial use that requires support from these surface waters. Now, it's no secret that Southwest Montana has experiencing some troubling declines in fish populations generally. They are not watershed or river system wide. However, they are very marked in certain stretches of the rivers within the Jefferson Basin. So you look up here and we've got these are the Montana Fish, Wildlife and Parks fisheries biologists' figures for the Middle River, the Melrose section, the section for which we have the longest running data set of fish populations in the Big Hole going back to the 60s. Those black dots each represent sort of an estimate of population in that section year to year from electroshocking surveys. You can see naturally, like every ecologic system, they fluctuate throughout the years based on drought, excess flows, things of that nature. And when we get all the way to the far left edge there, we see that we are in that level of historic low. It has never been this low in terms of fish per mile in this primary stretch of the Big Hole. When this decline began, generally speaking, in the realm of 7 to 10 years ago, that was coming on the heels of a really huge water year where we had a bump in populations. You can see we got way up on the edge of these historic highs in population numbers before gradually dropping down. And then in the years of, I believe it was 2015 and 17, we had some significant drought. We had an overabundance of fish per mile compared to historic average, particularly the brown trout, which spawn in the fall. And as a result of limited carrying capacity due to drought and low flows, hot water temperatures, and an overabundance of fish, historically speaking, we had some saprolegnia fungus breakouts and a lot of die-off in those years. That is not in and of itself an unnatural phenomenon in river systems, especially when your carrying capacity is overmatched by your populations. This is nature trying to achieve equilibrium, that pendulum swinging from an excess back to some sort of normal sustainable carrying capacity. However, the difference between that stretch of events and all the other years going back to the 60s is that once that happened, we did not see the bounce back in fish populations. And that began our multi-year decline to 2023, where we were at all-time lows of fish populations, specifically in the Big Hole, but also other stretches of the Jefferson Basin, the Ruby, and the Beaverhead, primarily downstream quite a ways from the dam. These impacts were widespread. It seemed to be somewhat exclusive to Southwest Montana, at least in terms of severity or dramatic nature of those declines. In 2021, we saw this unfolding as folks spending every day on the river. The fish population numbers reflected those observations that this decline was not really changing. It was continuing down. So in 2021, a group got together, concerned anglers, guides, outfitters, businesses, and citizens, and submitted a petition to the state requesting the formation of a joint effort to study and address these clear declines based on the data, particularly in the Jefferson Basin. A cold water fisheries task force is what we were calling it. There was no response received to that petition. As those declines continued and reached the bad news of 2023, FWP fisheries biologists in a meeting in Butte declared that we were now at historic lows, and they termed it a population crash in Southwest Montana. There were no silver bullet explanations, X factors that could be determined at that time from the fisheries biologists. And it was that moment that Save Wild Trout was officially born to address the lack of that task force and other data gaps within the basin in the absence of any other effort to do so. Then in 2024, Fish, Wildlife, and Parks, jointly with Montana State, due to public pressure about these declines, began an effort to conduct a 4-year research project. A 4-year study specifically to address adult mortality in the fishery, juvenile recruitment or lack thereof, and disease. To this point, no pathological cause has yet been identified. Histopathology efforts for tissue abnormalities and tissue collection are ongoing. The state sort of began an effort to collect data from individuals that were spending a lot of time on the river, in particular anglers, guides, and outfitters who were seeing many of these sick fish. You could see we've got some head necrosis, the rotting of the flesh in the eyes, on the top of the head. We've got some fungal outbreaks that are very dissimilar to the known saprolegnia fungus. And these things were widespread. We predominantly saw them in brown trout and whitefish. However, we did see them in rainbow trout too, to a lesser degree. We needed a repository for this anecdotal information to help FWP understand what they were dealing with. We began this sickfish.mt.gov website in order to report these fish, both pictures and locations of where they were spotted. so the FWP would get an idea of how frequently these fish were being encountered in the watershed. That is ongoing. So if you are an angler, guide, or outfitter, please mark that down and make sure that you're tracking the instances of seeing these kind of fish, because the more data points we have, the better we're able to understand and address issues. The one glaring deficiency, in my opinion, with this joint study was it was strictly biological in nature. By their own admission, the water quality was neither going to be collected nor assessed as an impacting factor on adult mortality, juvenile recruitment, and the like. So this really set off flashing neon lights in our head like, man, this project we're operating is critically important both on its own, but also to potentially help inform this fish mortality project in the lack of any other water quality analysis. I simply don't understand how we can fully assess a fish population's health without also assessing the medium in which they live. And so this is when the efforts of Save Wild Trout really kicked off and sought to address these data gaps within these systems that we were seeing the trout declines. And in these systems where others were not collecting water quality data, in these systems in which there was a biological mortality study going on. This was an opportunity for us to expand this project and not only address missing information, but also contextualize a biologic study and hopefully glean from it more information than just studying whether rough handling or keeping fish out of the water too long was contributing to this decline, the driver of the decline, or whether it was something else cumulative in nature. So in 23-24, Save Wild Trout really begins feverishly working. Their initial move was hiring Dr. Kyle Flynn, a PhD in ecology from Helena, to lead the science project. Dr. Flynn was the lead scientist and engineer at Montana DEQ for about 15 years, keenly familiar with numeric water quality standards, how water quality affects fisheries, and he was also an excellent data analyst. And since 2015, he has also operated his own consulting firm out of Helena, and that's who we hired to begin this full-blown science project throughout the Jefferson Basin. Not only to develop monitoring that was addressing missing pieces, but also to conduct the data analysis and compile reports that we can share with the public and agencies and other watershed groups. One of the initial efforts was 2023, a pilot project, much like the Big Hole River Foundation, where they had a limited number of sites. They deployed continuous data loggers in the river itself to track dissolved oxygen and temperature at 10-minute intervals throughout the summer season. By 2024, that project expanded exponentially to over 30 loggers throughout this entire basin to really understand diurnal fluctuations in dissolved oxygen and whether those were meeting water quality standards to support aquatic life. Secondly, was an incredibly expensive and important effort to visually document the entirety of the Jefferson watershed, all of those rivers, the Beaverhead, the Big Hole, the Ruby, and the Jefferson, with drone-based thermal imagery. So these top pictures, you could see the coloration within the topographic map there. And every mile, every inch of these watersheds was flown multiple times with this FLIR technology and mapped. And that effort was very important, very expensive. Over $350,000 were raised to conduct that mapping, watershed mapping. One of the things we're trying to raise money for currently is we have the product, but we need a permanent online home so that folks can access this and tool around in it, both the general public, but also researchers, agency folks, and restoration experts. It has already borne fruit in that if you look up here at this top left map, you can see the orange right through the middle of the river, and then the yellow strip down the right bank, river right bank. If you look just upstream of that, you could see that dark cold water coming in. This allows us to understand not only how hot is the main stem of these rivers getting, but also where are these important mixing zones where you're getting cold water influx, whether through springs or creeks or sloughs returning, and not only the effect that mixing has on overall water temperature of the main stem rivers, but also how long does that benefit last downstream? You can see that yellow line. That's a significant benefit downstream in terms of hundreds and hundreds of yards. That product right there can help inform where we're doing restoration work, where we're doing changing points of diversion for irrigation, where we're considering putting a pump in for irrigation. And it's allowed, to a small degree so far, the folks at FWP to request specific tiles and understand if we put the new point of diversion here, what impact will that have on the benefit we get from that cold water mixing. But if we move it to the other side of the river, we can take hot water out, leave that cold water in. So it's really important to us going forward to raise the money to get a permanent digital home for this product so that you, the lay public, but also anyone interested, in particular folks doing restoration work, can help inform and prioritize the bang for the buck of their projects based on this kind of data. And then finally, just a quick mention, you can see these data loggers down here. They're strapped to a brick, hidden in camo burlap, and those things live in the river from the end of June through the 1st of October, give or take a couple of days. And that allows us to track diurnal changes and 10-minute intervals of dissolved oxygen and temperature for the period that DEQ is concerned with for determining impairment of these beneficial use supporting parameters. Okay, what do the numbers mean? Well, as we know, I think intuitively, if I haven't made clear, dissolved oxygen is necessary for the survival of aquatic life and their metabolic processes. Just like human infants, juvenile fish and aquatic life is more sensitive to levels of dissolved oxygen. DO is directly influenced by eutrophication, that process we discussed earlier of plant growth, photosynthesis, and respiration. Warm water holds less DO than cold water, so that's a secondary effect of climate change as water supplies are reduced and the temperatures increase. That water is incapable of holding more dissolved oxygen compared to cold water. And there is a water quality standard for dissolved oxygen to support aquatic life. That standard is 5 milligrams per liter. And really, it's 8 milligrams per liter in the water column, and that allows us to achieve 5 milligrams per liter in the substrate, the river bottom, where fish eggs, juvenile fish, and bugs live. So here's an example from 2025. I just finished processing this data set from the Big Hole at Mud Creek Bridge. This is one of our long-running sites through the foundation previously and ongoing site now through Save Wild Trout's efforts. This change in the hydrograph, the graph for dissolved oxygen tells you kind of how high it gets during the day, how low it gets at night. And I've superimposed this red line here. That is 5 milligrams per liter. So this gives us a good idea of how frequently we're dropping below that water quality threshold for dissolved oxygen designed to support aquatic life, how long we're staying below that threshold, hours long. and how long throughout time. This is the month of September. I believe at last count, this was about 22 days out of the month of September dropped below that water quality standard for dissolved oxygen to support aquatic life. It did the same thing during August and July. So that gives you an example of how often we're seeing problematic levels of dissolved oxygen. Let's talk about real quickly the other nutrient thresholds, currently numeric standards. This is the best available science for determining the levels at which we can expect negative impacts on beneficial use. If we're above them, we should be in good shape if we're below them. Those thresholds that Dr. Flynn was actually party to developing at DEQ are as follows. For total nitrogen, it's 0.3 milligrams per liter. Total phosphorus is 0.03 milligrams per liter. These are very clear numeric scientific thresholds that make it easy to see. We can superimpose that line just like our dissolved oxygen on this graph and see how often are we getting above that line, how often are we staying below it at every site that we're sampling throughout all of these rivers. A quick note, in 2021, Senate Bill 358 was signed into law attempting to remove those water quality standards numerically and go back to qualitative or narrative standards. Fortunately, there was legal pushback against that effort to become less protective in our water quality standards. And the appointed nutrient working group was unable to come to a consensus on what that revocation should look like as applied to actual water quality on the ground. That effort stalled. But unfortunately, then again, in 2025, we had House Bill 664. That bill did achieve the removal of numeric water quality standards for Montana. Unfortunately, we are the first state to roll back protective water quality standards to something less scientific and less protective. And we don't know exactly what that's going to look like yet. DEQ is still attempting to design and define what that looks like as applied to water quality standards. Some potential qualitative measures could include the percent coverage of the river bottom of algae growth, the mere presence of algae blooms, and shifts in macroinvertebrate communities, aquatic bug communities. And unfortunately, neither of those efforts is going to be as protective or preventative as numeric standards were and are. Numerics give us a very well-defined scientific metric to help understand when our river conditions might be becoming harmful to beneficial uses before those negative impacts become apparent and extensive. They are therefore preventative as opposed to reactive. Once those algae blooms are taking place in river-wide, qualitative or narrative standards let us say, hey, there's algae, we must have a problem. So we'd like to be going back to the science-based standards and acting in a preventative, proactive way to protect these delicate and important resources. What have we found? We've talked about the numbers, we've talked about what we're looking at, where our sites are, how frequently we're visiting, what we're sampling for, what the lab's analyzing for. In the Big Hole, which is where we have the longest running data set currently, we have regular, what I would term chronic exceedances for nitrogen and phosphorus, documented over 6 years of a DEQ-approved program on the Big Hole. At some of these sites, it has been 100% of the time sampled over 6 years have exceeded for these parameters. We have dissolved oxygen minima, the lowest level hit at night, regularly dropping before water quality standards to support aquatic life and juvenile fish. We have seen more frequent, earlier beginning, later lasting, longer lasting algae blooms. You could see some of these pictures. The top picture is the lower Big Hole. The middle picture there, it's a little harder to see. It's not quite as bright green, but that is bank-to-bank 100% coverage in the upper Big Hole. Next to that, the bright green is an explosive neon green algae bloom that took off on the Boulder River, tributary to the Jefferson. That algae was attached to everything that wasn't sand. The only thing without that neon green, you can see that brown line, is sand. And then we got Mud Creek Bridge, where we have a chronic issue with exceeding nitrogen and phosphorus standards, dissolved oxygen levels, water temperature issues, and algae growth issues. I think the bottom line is that it's clear, no matter which metric we use, we have credible evidence of impairment for water quality that's not supporting aquatic life on the Big Hole. If we use numeric standards, we've documented that. Chronic exceedance for nitrogen and phosphorus at some sites, low dissolved oxygen levels that are harmful to aquatic life, and our bug work has shown shifting aquatic invertebrate communities that are becoming dominated in terms of percent of biomass within that sample by species that are more pollution tolerant, like certain midges and aquatic worms, annelids, rather than our very, very beloved, important, and sensitive species like ephemerella, your PMDs, or Plecoptera, your stoneflies. Then again, if we use narrative standards, I think it's clear that there's credible evidence of impairment as well. Presence of the algae blooms, the scale, the percent coverage, the neon green explosion, and of course, all these things reflect the existing fishery problems of depressed populations as well. It's really hard to visualize what excess nitrogen or phosphorus looks like in water. So I wanted to put just a real quick screenshot together. This doesn't include 2025. I haven't quite submitted that data yet. That's coming up next month, in just a couple weeks. But I wanted to give you some kind of visual idea of how frequently we're exceeding for nutrient pollution in the Big Hole. We've got the site, the date, the time the sample was taken, the column by year. Notice that it's only 3 months each. I only wanted to discuss those months for which DEQ is assessing for impairment, and those are those base flow months of July, August, September. The brown is any reading that was, or the tan rather, was any reading over those numeric thresholds. Yellow was anything double or above. And then 3, we've got red, which is triple or above the thresholds for nitrogen or phosphorus, or both. You can see some regular offenders here, primarily in the upper Big Hole, Mud Creek, Wisdom, that area, year after year. And this is just a graph to kind of explain where that problem is in terms of a percentage of frequency. I think it's notable that some of our main tributaries in terms of volume, especially the Wise River and our main stem site at the very headwaters, our control site at Skinner Meadows, have never exceeded for either nitrogen or phosphorus during those summer growing months. These figures don't include the months of April through June or October. That's outside DEQ's impairment assessment time frame. It is certainly plausible. You can see some of the top figures there are, about a third of the time or less. Big Hole at Twin Bridges, that's our lowest site, Calsta Bridge, Maiden Rock, Deep Creek, Mud Creek, North Fork of the Big Hole, Wisdom, and Jackson. It's plausible that those lower river figures not exceeding all that frequently, no more than about a third of the time sampled, is because that's where our huge algae blooms are generally taking place, sometimes 20, 30 miles long in that lower river. So it's plausible that those lower readings of nitrogen and phosphorus are due to plant and algae uptake of nutrients within the watershed. And then the samples we take in the bottles show what's remaining beyond plant uptake. And certainly the location and extent of those blooms are reflective of both our water quality samples, but the locations of where those blooms have taken place in 2020, 23, 24, and 25. They are frequent and getting more frequent, it seems. So what did we do about what we were finding? The goal of both the Big Hole River Foundation prior to the merger and now under Save Wild Trout is data collection. It's good science, credible science, collected according to DEQ state protocols, utilizing their labs, getting approved by those technical advisors, and advocating for using good data to make well-informed management decisions. However, our data is freely available to anyone who's interested, researchers, agency folks, and as a result of what we found over the first several years of state-approved collection, Upper Missouri Waterkeeper took that data set on the Big Hole and filed a petition with DEQ, compelling them to review the best available data and make an impairment designation decision. That was in February of this year, 2025. It is an ongoing process, and I quickly want to address some misinformation that's been out there that the reason we have not yet succeeded in this impairment petition is due to some kind of validity issue or credibility issue with the data that we have submitted. That's patently false. DEQ themselves has come out and said that there were zero quality assurance issues with our data. They've approved all of it. This is a legislative issue. This is due to the removal of those numeric water quality standards. So this is an ongoing process. And in fact, when DEQ is able to define what the application of narrative standards look like, then we have requested that they reassess our impairment petition based on that narrative criteria. And we have spent this entire year providing them alternative data sets, including aquatic plant visual assessment forms, photos and drone footage of the algae blooms, biweekly reports of the extent, duration, and location of algae blooms, as well as reformatting the entirety of our macroinvertebrate data to meet their requested needs for reassessment. So that is an ongoing process, and I just wanted to clear that up. Why did we pursue a petition? Why did we think it would be helpful to get an impairment designation placed on the Big Hole? First and foremost, the data clearly show that it's warranted. Beyond that, it's not for the sake of saying something is impaired, it's for the sake of what that official designation, the path which that designation starts us down to address it and eventually improve it. DEQ would need to create DMDLs for mainstream Big Hole nutrient pollution. What that would do is essentially make it more difficult for what we all consider a threat in rural Montana is unrestricted development, in particular for our sensitive resources. Cows, not condos, right? So if there was an impairment designation, potential land use changes or development like subdivision or golf courses would have to prove beyond a reasonable doubt that they would not impact an existing impairment or make it worse. And that would force a more stringent permitting process for development along a watershed. Secondly, it would oblige DEQ to narrow down those influxes, those sources of nutrient pollution, and work with landowners and watershed groups and restoration groups to improve those issues. It would oblige DEQ to find and direct more resources to addressing this defined issue at this point. And most importantly, or probably most practically, I should say, this is a new pot of funding to pull from for groups that are already doing good restoration work, like the biologists at FWP, the folks at the Big Hole Watershed Committee, some of the folks at Montana Trout Unlimited that are working in a smaller scale to address some of these problems, primarily on tributaries. This would provide us a bigger pot of funding to pull from for them to continue and expand projects that frankly, that they already would like to do to improve fish habitat and resilience, and river conditions, water quality conditions. So we don't want to see any more of algae blooms like this. We would like to see the improvement, not just the declaration of impairment. And that's really the motivation behind this petition process, is to acknowledge the reality of current conditions, compare them against standards for water quality, assess whether they're meeting those standards or not. In this case, they're clearly not. Let's get started down the path of rolling up our sleeves and addressing it and scaling up some of the good work that's already taking place so that we can have a river-wide impact on improving fisheries, improving aquatic life health, and the general condition of water quality. Now, as I said, that was the big hole. We have the longest running data set on that river. However, I do want to go over what Save Wild Trout's initial effort on the rest of the rivers in the Jefferson Basin have found. This was released in the summer of 2025 in a public presentation up in Helena by Dr. Kyle Flynn and myself. And he compiled all of the data sets collected during the 2023-2024 field seasons and created a Jefferson Basin abiotic report. And two things out of this, I don't want to spend too much time on it. One is the map to see how many more sites we've adopted to really get a good, clear resolution picture of what water quality looks like throughout this basin on multiple rivers. And then the really important thing that Dr. Flynn found in his research project, 3 of 4 Jefferson Basin rivers showed extensive thermal and oxygen impacts in 2024. And those rivers are experiencing and exhibiting eutrophic conditions, nutrient pollution, and the effects of that stressor. The Beaverhead River, all sites monitored for chronic temperature, which is water temperatures above 70 degrees, or acute temperatures above 77 degrees, which are harmful to aquatic life. Every site on the Beaverhead sampled, with the exception of the furthest upstream site at Henneberry, failed to achieve water quality standards for temperature for chronic temperature conditions. And the lower sites, unsurprisingly, the lower 3 sites exceeded those acute water quality thresholds for temperature. Similarly, with dissolved oxygen, that 5 milligram per liter failed in the lower 4 sites of the Beaverhead. In the Ruby River, this was our least compromised river. I think, you've got a generally intact riparian area, some coverage, shade over a small river. You've got the positive influence, dissolved oxygen, and cold water discharge of the dam. However, those benefits don't last all the way downstream. They have a demarcation line where those benefits are lost. And you've got a very turbid Ruby River, which to a degree, if you are turbid, you're allowing less sunlight into the river for algae growth, and that can be reflected in some of these conditions. However, we still do have water temperature issues. The lower 4 sites failed to meet chronic water quality standards for temperature, and the lowest site exceeded that acute threshold of 77. Then the big hole. Every site monitored, there were 10 of them, exceeded the chronic threshold for temperature. The upper 4 sites and the lowermost site on the big hole reached above 77 degrees. And then we had some dissolved oxygen issues in the upper and lower 3 sites of the big hole. Similarly, on the Jefferson, I don't think a surprise to anyone, all sites exceeded both for chronic and acute water temperature to protect aquatic life. And all sites except the site in the Lewis and Clark Caverns near Lime Spur, where I think we get some groundwater influx there, failed to meet dissolved oxygen levels capable of supporting early aquatic life. So this issue we're seeing in the Big Hole also seems to be apparent in sections of the rest of these rivers. And I think it coincides with where we're seeing some fishery problems. So this is notable. When we are finished processing 2025's field season data, we will compile a similar abiotic report for that year. 1 year report is great, but that can be a fluke. 2 years starts to begin a trend, and a lot of what we've seen in 2025 reflects exactly what we saw in 2024. At this point, I want to take a break, and then we're going to talk about benthic macroinvertebrates, bugs, i.e. fish food. Good morning. My name is Brian Wheeler. I'm the program director of Save Wild Trout. And we've been talking today about water quality monitoring projects taking place in southwest Montana in the Jefferson Basin, facilitated and run by Save Wild Trout. And I want to take a chance to talk specifically about our macroinvertebrate monitoring program, bugs, i.e. trout food. And this next stretch, we're going to chat about what does our project look like, why is sampling for bugs important to monitor water quality, and what we might do with that information when we dive into it and see what it says over time. So we want to talk about benthic macroinvertebrates. What does that mean? Benthic means bottom dwelling in the stream bottom, and macroinvertebrates, it's an animal without a backbone that's visible to your naked eye. So if you've ever been out fishing and you're trying to figure out which fly to tie on, maybe flip some rocks over to see what bugs are in the river, and what stage those bugs are in their development. You might see a stonefly, a caddisfly case stuck to the rock, a mayfly frantically swimming away. That gives you an idea of visually what bugs are actively on the menu for trout. Those bugs are also very important for evaluating water quality because mayflies, stoneflies, and caddisflies in particular are quite sensitive to pollution and habitat degradation. The evaluation of their relative abundance, their diversity, is often used to determine whether your water and habitat quality is meeting the needs of aquatic life as a beneficial use. Got some great images here from the past several years of our work. We've been fortunate to have a lot of community volunteers. These two gals were my rock stars, staff at Winston Rods there in Twin Bridges. They wanted to come out and have a personal hand in sampling on their backyard, the Ruby River. And so we scrubbed rocks. Every rock that's bigger than a golf ball, we scrub with a brush. We pick it clean, and then we dig down into the substrate about 1.5 inches or so until that water runs clear. And then we take whatever is collected out of that sample and put it into a jar with 99% isopropyl alcohol to preserve the sample. And we do that 4 times at each site. 4 replicates allow us to reduce some of the variability if we were to say just take 1 sample or 2 samples or even 3. Some of these images on the bottom, obviously up close microscopic images. We've got a great entomology partner. Senior scientist Brett Marshall owns River Continuum Concepts in Manhattan, Montana. And he's been our partner with project design and data analysis since we began through the Big Hole River Foundation and continued and expanded through Save Wild Trout going back to 2019. And Brett not only categorizes and identifies our subsamples, he also gets me these amazing pictures for us to use in presentations like this. We got golden stoneflies. We got a Mother's Day caddis in the middle in its case. And the only one not from the Jefferson Basin is that one on the far left. That's a October caddis from Yellowstone National Park, a species we have here, but that particular specimen came from Yellowstone Park. And then right above that, we got a pretty amazing image we caught while sampling this year of that's a salmon fly, but one you rarely see in that color variation. Those big nymphs, The big mature nymphs, those are generally jet black or really dark brown. This one happens to be caught in our sample during a tenaral phase. So it has shed its exoskeleton and its skin has not yet hardened back into its new, bigger exoskeleton. This can last a couple of hours and then it'll be that color you're used to seeing with big salmon flies, the dark color. So, really neat what we're able to see. Um, it's a lot more visual than water monitoring for things like nitrogen and phosphorus. Um, and I get a lot of volunteers very interested in helping with this part of the program, in particular, fly fishermen and women, because they want to know what's in the river and help them with their bug identification. We want to know what's in there, how that's changing for its impact on water quality. So, a sampling day on the river takes place. They're exhausting. This year, we had 13 sites total throughout the entirety of the Jefferson Basin on the Big Hole, the Beaverhead, the Ruby, the Jefferson, and the Boulder rivers. And we use a Hess sampler. You can see in the top corner there, Merle, one of our entomologists, um, is using the Hess sampler. It's a third of a square meter within that metal cylinder, and it's got a tapered dolphin net down to that collection cup and a screen in the front, so that current moves through and pushes everything we dislodge from the bottom into that collection cup. Like I said, we do that 4 times at each sample site, and you could see the collection. This year there were 52, I believe, samples preserved in 99% isopropyl alcohol. Um, Pretty sure my truck still smells like that. And then those were delivered to the lab at River Continuum Concepts for ID and analysis. Got some great pictures, kind of this traditional dark brown or almost black looking salmon fly nymphs. You can notice there's some different sizes. Those salmon flies range, from a couple years cycle to 4 years for the true Pteronarcis californica, the giant salmon fly. So any given year, there's some overlapping generations of subspecies of salmon fly that might hatch. And so you get multiple size and age classes, which is really neat to see within a sample. And then, of course, next to that, we've got the classic salmon fly perched on a stick. This bug has just hatched. It has dried out its wings. It is ready to mate and then do its flight to lay those eggs in the river and start the next generation all over. So, changing gears here. Salmon fly is obviously a renowned insect hatch in the fly fishing world. And even if you're not into fishing, it is truly one of the most incredible natural phenomenons you can witness on a river. The emergence of this bug, their shucks all over the riverbank, the mating, flying, egg laying hatches moving upstream, bugs crawling down your shirt, up your sleeves, behind your glasses. Thankfully, they're harmless. Um, it is unparalleled in the world of fly fishing. And people have noticed a decline. This is one of the reasons that we began this bug monitoring component of our water quality project, to attempt to address this public concern, this observation, this anecdote over decades, that the hatches just aren't what they used to be. We're not seeing the same number of bugs. It's not as prolific. It's not as widespread along the river, not as long lasting. And that issue is not exclusive to the Big Hole or Southwest Montana. As you can see here, these questions are everywhere in both standard newspaper media and fly fishing media. The scale of the importance of this hatch is highlighted here. It's the most significant event in the natural world of trout. Salmon fly hatch, it's the lifeblood of some of these rivers. This is when the most people show up to fish. But what's happening to these bugs? It's not just in Montana, Utah, Colorado, Wyoming. They're noticing these declines in this famous salmon fly hatch as well. And in fact, that has been corroborated by quantitative science. Um, at several streams, 10 in fact, in the West, the famous sort of, I guess if you would call it the Bible Belt of Rocky Mountain West fly fishing, is this stretch through here. And 10 of these famous Western trout streams have experienced declines or localized extinctions of salmon flies. And you can see all the entomologists at the bottom there, including a very, very good Montana biologist and entomologist, Dave Stagliano, as well as an up-and-comer, Jackson Burrell, with the Salmon Fly Project, who we've worked with on the Big Hole, documenting some of these salmon fly declines in famous rivers throughout the West. So what are some of the potential factors causing these declines in this world-famous hatch throughout the Rocky Mountain West? Certainly, a lot of them have overlap with all aquatic life, especially our fish. Warmer water temperatures, just like cold water species like trout, grayling, char, um, macroinvertebrates, in particular the stoneflies and the salmon fly, have a maximum tolerance for water temperature, both chronic exposure and acute exposure. Those warmer temperatures, often caused by low flows and droughts, reduction in habitat, low dissolved oxygen levels, as a result of the next one, nutrients. I've got everything that we've documented or questioned here in the Jefferson Basin in southwest Montana as a contributing factor in our fishery declines are highlighted in black here. And these are the same things that are likely affecting anecdotal evidence of declining hatches. Low dissolved oxygen, nutrients, eutrophication, sedimentation, loss of habitat. Diseases I have in black there because we're not sure yet with these fish. That's not been identified in bugs, but it's a potential. These, again, as we discussed earlier, these are stressors, and then things like warmer water temperatures, low flows. Those are stressors on river conditions that result in the response of algae blooms, low oxygen levels, and lost habitat. So keep that in mind. Stressors in response, stressors in response. So some of these stressors, low flows and sediment pollution. That upper picture there, I took that while we were sampling. That's up by Wisdom when we got at about 2 cubic feet per second of volume. Very little habitat left in the river there. Certainly at low flows, we have reduced channel width, as that clearly shows. Automatically, that's less habitat, both for fish and insects. If you don't have the volume and flow velocity capable of flushing the river clean, flushing the sediment out of the interstitial spaces between rocks, the gaps between rocks and cobble, that's where stoneflies live. If those fill in due to low flows and no flushing flows or weak flushing flows, again, less habitat both for the bugs that trout eat as well as juvenile fish and eggs. And then, of course, higher temperatures, higher water temperatures, you get more algae. Higher water temperatures, nutrients, you get more algae. You get lower dissolved oxygen. You get less habitat. So the key questions we're trying to answer with this macroinvertebrate project: is sediment building up or algae choking out good insect habitat? We haven't really quantified a sediment issue to this point. Certainly in some places there are, but in the main stem, that hasn't been a real or significant factor, at least in most locations. But the algae is certainly choking out good insect habitat. And how is this affecting macroinvertebrate abundance and species diversity? Well, in some of our sites, we have seen a reduction in some of those sensitive species like your mayflies and stoneflies, and we've seen a simultaneous increase in some of the pollution-tolerant midges and aquatic worms. So the answer, at least partially, to some of these questions is, yeah, we're seeing an impact from low flow and sediment. Nutrients and oxygen. This is the the main focus of our water quality monitoring program, but you can't divorce these things from one another. They all have a cumulative impact on aquatic life as a beneficial use. More nutrients. The pictures show we've got these extensive neon green algae blooms. Like we talked about earlier, the processes of photosynthesis and respiration and then decomposition of the algae reduces dissolved oxygen. And then, of course, it chokes out good cobble and good habitat. So, what are we trying to do? Well, we're trying to document how low are those water oxygen, those dissolved oxygen levels getting. We're beginning to do that with our continuous data loggers. And are those levels correlated with low insect abundance and diversity? Well, the only way to answer that is if we're taking both dissolved oxygen readings and macroinvertebrate samples at the same location year after year. And so that's what we're working on. Temperature. I don't think it's a surprise to anybody that in these last several years, water temperatures have been excessive, to say the least, reaching near 80 degrees plus in some of the reaches of these main stem rivers. Um, I think inherently we all know that's bad for trout and aquatic life, but there are some quantitative figures we can put to that. Salmon flies, like our preferred native and wild trout species, don't typically live in streams where average monthly temperatures are greater than 65 degrees, or those instantaneous acute water temperatures are reaching 77 and above. Obviously, trout struggle in those temps as well. Well, what are we seeing in the big hole? This is again where I have some data to go by, some consecutive years of data. We've got our mean average water temperatures reaching right at or just over that 65-degree threshold for salmon flies, and certainly we're reaching or exceeding that acute threshold of 77, just like we have for protecting our fish populations. Um, Melrose, Dickey Bridge up above Wise River, Big Hole at Mud Creek Bridge. These are some disparate readings, but it gives you an idea of kind of year after year where and how frequently we're exceeding or getting really close to those thresholds that salmon flies have. We can't do a big report on a single year of data. I suppose you could, but it certainly wouldn't be worth the cost to do so. So while we began this project in the Big Hole in 2019, we wanted to get a sort of benchmark released to the public that would begin to build out the framework we would use for future comparison in our bug monitoring effort. So what we did is we took the initial 4 years of our bug work on the Big Hole, and we conducted, we commissioned our entomology professional to compile all that data into a 4-year bug report based on 2019 through 2022 data on the Big Hole that we collected at the same sites. In that report, what we wanted to do was get a sort of rough baseline, the first 4 years of data. We wanted to take into account historic data where possible. Obviously, it was difficult to do so because since the 60s, methods change, locations aren't consistent, they're irregular, timing's irregular, conditions have changed over all those years. So it's hard to directly compare, which is why we wanted to set this sort of benchmark metric and use the same methods, locations throughout time going forward. We wanted to discuss tolerance limits, pollution tolerance limits of the primary insects, in particular that anglers care about, the salmon flies, your golden stones, your little yellow sallies, PMDs, your green drakes, those really important and cool hatches that cause folks from all over the world to visit these famous rivers in the West. After that, we wanted to begin to build a framework for future comparison. And what I mean by that is let's begin to identify what the expected ranges of these bugs are in terms of quantity, the expected diversity, abundance of different species within a site sample set. And then, of course, when we're able to do this over time, we're able to track the shifting response of those aquatic invertebrate communities to changing water quality conditions and in particular water pollution. And as we've discussed, these tolerant species like certain midges and worms um, becoming more dominant as a percentage of the sample compared to, say, our sensitive species like the salmon flies and the mayflies. Again, we've got some awesome pictures here. The top one was from a sample. That's a stonefly color you do not see every day. That kind of goes back to that early salmon fly, cool orange, black color. This is a bug who has recently shed its exoskeleton and kind of like a crayfish does. It's molted and it is very soft and vulnerable at this point until that outer layer hardens into its new shuck. So pretty neat to see that in the wild because that doesn't last more than an hour or two, couple hours. And then we've got a really wild looking caddis down there underneath. We can't talk about all this work being done without talking about how much it costs to do it and why Save Wild Trout is taking up that mantle. Um, as we've discussed, this is the data gap. Nobody's consistently collecting this data over time and space at the same locations. That's missing pieces for resource management. And in order to do so, this is what our project looks like. This is a snapshot of what 2025 and going forward looks like. We have 25 of those continuous data loggers on all rivers in the Jefferson Basin: Big Hole, Beaverhead, Ruby, Jefferson, and Boulder. We have to clean those regularly. They experience biofouling. Algae growth can take place on these loggers. So every 2 weeks, we're out in the field, either myself or volunteers, cleaning those and making sure that our readings are correct by taking field measurements as well with a calibrated meter to make sure things are reading correctly in unison. Um, in addition to those 25 data logger sites, we got 19 water sample sites. In 2025, what that looked like was 117 bottle sample sets for our various nutrient analytes, sediment analytes, and also field blanks and field duplicates for quality assurance and control measures. Um, that handheld field meter, we took 214 individual readings. Those are important as data points both on their own for when we submit this to the state, but they're also super helpful for making sure we're not getting drift in our data logger readings for dissolved oxygen and temperature. And then, as we've said, we've got 13 macroinvertebrate sites, 52 bottle samples, 4 replicates at each of those sites. That took about 2 weeks of rock scrubbing in 5 different rivers. And in order to do all of this, we drove 10,000 miles this summer just checking and collecting water equipment and samples. Thankfully, I was able to engage 12 volunteers locally from around the region within that Jefferson Basin, from small businesses, fishing-oriented businesses that wanted to give something back, individual guides, and friends and students and folks interested in environmental sciences have reached out to volunteer. And the direct fieldwork expense, what this program looks like in terms of a budget, is $65,000 annually. That's no overhead, salaries, time, or anything. That's simply what the direct fieldwork and data analysis at the lab costs year in and year out. Anything you want to do beyond that costs more. You want to add a site, add a sampling event, add a replicate, or compile a report. That all costs above and beyond. Um, so it's a dedication because it's necessary. Nobody else is doing it. It's an important data gap to address, and we really, really endeavor to do this work um, because it gives us a framework to impact, hopefully, um, management level change for natural resources in our rivers. Um, in particular, in the face of anthropogenic climate change and increasingly unrestricted development that threatens these cherished natural resources. So what do we do with all this stuff? Both our water quality work and the macroinvertebrate work, that budget that we're fronting every year to provide the state with data that they need to make good decisions. It boils down to these following bullet points. Our goals with this project, what success in monitoring water quality looks like is the following. First, we got to document. We got to document current conditions, emerging issues, improvement or deterioration over time. As we do that, we're able to define a baseline of watershed health. What does our equilibrium look like? What do our deviations from equilibrium look like within a watershed? Doing this allows us to identify trends over time. Um, with each passing year, this data set just gets more and more and more important and valuable for identifying trends over time, for reducing the variables of year to year conditions. It allows us to identify both problem areas within the watershed for pollution and conditions which may not be supporting aquatic life. It also lets us identify where the refuge areas are that fish may be escaping to when conditions get bad. Equally important for us to define both problem areas and refuge areas that can help inform resource managers with information to, say, determine what fishing restrictions should look like. Um, Next, we got to provide this data to anyone interested. We don't collect data for data's sake. Yes, it's important for the historic record. One of the challenges when we began this project was as we began collecting these data sets, we didn't have anything to compare them against. There wasn't a historic record to say, are we better, worse, or about the same as what it was 30, 40 years ago? It's speculation at this point. However, we do know what from here forward looks like. And if I don't achieve anything else in this role, hopefully the next iteration of me that comes along in 20 years and takes up the mantle of monitoring water quality, bugs, and fishery populations will have that historic benchmark against which they can compare. Are things getting better? Are they getting worse? And what are the land use changes along the way that have happened that may be influencing improvement or deterioration? So certainly resource managers benefit from the provision of this data set at the state level and agency level. Researchers like the graduate students and supervisors, professor supervisors at MSU, um, as part of the joint fish mortality study, will benefit from this kind of work. Grad students that are interested in fleshing out some of these questions in more detail that our data may um, trigger in graduate students, that's useful for understanding our resource better. And then finally, groups that are doing restoration work currently that we'd like to see scale up that restoration work. This data set can help narrow down those areas where we might get the best bang for the buck, um, where where projects should go if you've got a limited budget, but also by defining impairment in some of these sections for certain pollutions like nitrogen and phosphorus, we're able to increase the pot of funding that groups like those can pull from to do some of these habitat improvement projects. Um, Certainly, part of this presentation is advocacy. Any public outreach and education effort is advocating both for understanding of the importance of water quality as it relates to natural resources we care about, but also as it relates to other uses like irrigation and drinking water here in Butte and recreation a healthy river for aquatic life is a healthy river for all those other beneficial uses. And we want to advocate using good data to make good informed management decisions to protect all those beneficial uses, not just one or two. Um, you can't have advocacy and good science driving management decisions without accountability. And part of this quantitative effort that we're undertaking is to determine if water quality standards are being met to support aquatic life, and accountability for folks charged with those decisions if those established scientific standards are not being met. And that explains to you like petition processes for repairment and things like that, that legal advocates for water quality, like Upper Missouri Waterkeeper, are undertaking, utilizing these data sets. And then finally, as I've noted earlier, the goal is not just to shout or point fingers that we have an impaired reach of river or river as a whole. The goal ultimately is to use these steps to identify where those areas exist, begin to address them, get us started down the path to improve those impairments, and eventually to get to the point where we're no longer impaired. And the goal of that, of course, is not only um, immediate. It's also because with these resources, it's not ours, it's just our turn. And part of stewardship is improving things for future generations, not just maintaining status quo, maintaining resources hanging on by the skin of their teeth. It's about actually shepherding them in a healthy way that we can pass on to future generations the experiences and joy we've derived from these natural resources. Bottom line goal, as we noted earlier with the Clean Water Act and surface waters of the United States, we want to make sure that all the rivers in the Jefferson Basin, and frankly others where data is lacking, as surface waters of the US are capable of fully supporting all the beneficial uses demanded by the Clean Water Act. And that is the goal of our project, and we hope that you will join us in supporting this important work. Again, this is useful for all who are interested in protecting natural resources, and in particular for state agencies carrying the mandate to preserve and protect those natural resources to support multiple beneficial uses. You can help in a few ways. Obviously, tax deductible donations to this work can be given on our website. We've got up here. Um, Currently, we're conducting a raffle with some really stellar prizes donated by groups like Winston, Sims, Yeti, some individual fishing guides who care deeply about this work that have donated a day on the river with them throughout the state, and various other prizes. You can check that out on our website, buy some raffle tickets, and support this work. The proceeds go directly to the water quality monitoring work we're doing. Um, Certainly, you get on that website, you can sign up for our email list, keep track of what's going on, keep track of potential public comment opportunities. And speaking of public comment, one of the biggest things we can do as individuals is directly reach out to, write, or call your legislators and tell them that cold water fisheries are important to you, and the myriad ways in which they are important to you, whether it's economic or ethical or just sheer enjoyment of being out on a water during a hot summer day. It's important for our legislators and folks charged with decision making and budgeting hear from you about how important these natural resources are to your life and livelihoods. And frankly, let them know that you're concerned about rolling back water quality standards, because we want to see these things not only maintained but improved and stewarded for future generations. Thank you for your time.